Hello, my name is Aadit, and in this video I will be introducing you to calculus and why we need it and what it's segregated into. So let's start. Let's say we are trying to measure the motion of a car that is accelerating. So we've measured a graph where we know the speed and we know the time elapsed. So now we want to try and find, let's say, the acceleration of the car at, let's say, this point on the graph. How would we find it? If we were to graph it, we would draw a tangent to the graph. So something like, this is inaccurate, something like this. Something like this. And then we would measure the change in y and the change in x, which we know is delta y and delta x, where delta means the change in something, so the change in y and the change in x. And we can use the formula for the slope or gradient, which is delta y divided by delta x. But if we need to find the gradient where we're not asked to graph it, how would we find it if we're just given the speed and the time? Well, that's where differentiation comes in. So differentiation is the concept where we want to find the gradient of a certain point on a curve that is usually the instantaneous rate of change graph, and that's where we use differentiation. So we already know how to find the gradient for a straight line graph. We know that for this graph, for example, the gradient is going to be the delta y by delta x overall for the entire graph, because the gradient is the same. But for this graph, the gradient continuously changes. That's why it's curved. So at this point and at this point, the gradient is very different. Over here, the rise may be higher, and over here, the run may be longer. So we would use differentiation to try and find the gradient at a certain point of a curve where delta x and delta y are extremely small. So let's say this point and this point. So the change in y and change in x is almost not visible at all. So over here, we would express this as dy by dx, which is the differential notation of the change in y by the change in x. But have you noticed how similar this looks to the original notation of delta y by delta x? How is it similar? Well, delta starts with a d, doesn't it? And that's before y and x, was before y and it's before x. Well, d is before y and it's also before x. And d is the first letter of delta. So maybe the notation is trying to say that we are measuring the change in y by the change in x, where the change in y and the change in x are extremely small. Another way of expressing this would be if the equation is y equals to something or fx equals to something, then the differential of y would be y prime, and the differential for fx would be f prime x. This basically means that this is the differentiated version of fx, the differentiated equation for fx. And this means this is the differentiated equation for y equals to something. Here's an extension question. I know I haven't taught you how to differentiate yet, the actual maths behind it. But what if we were to differentiate a straight line? What if we were to differentiate this point on a straight line? Or actually any point works because they all have the same gradient. What do you think would be the outcome? Because when we draw a tangent to a curve, what do you notice? What are we trying to do? We're trying to find the change in y and the change in x, and we're trying to find the gradient of a certain point on that curve. But the gradient is a straight line. So we're going from a curve to a straight line. So if you've learned about quadratics, you would know that the graph for quadratics probably looks something like, it's a rough sketch, something like this. And if you've learned a cubic, then you would know that a cubic probably looks something like this. So when we differentiate a quadratic, we get a straight line. If you were trying to find it at this point, for example. What if we were trying to differentiate a cubic equation? Would we also get a straight line? So if we were to differentiate it at this point, would we get a straight line just by differentiating it once? I want you to think about this before the next video uploads, where I'll actually be teaching you how to do it. So for this video, this should be enough for differentiation. Now let's go back to that graph. So let's say we wanted to find the distance that the car traveled instead of the acceleration. How would we find that? Well, if you've done a little bit of physics or you've learned this in maths, then you would know we'd have to find the area under the curve. So this area right here. But we don't know how to find the area under a curve. Till now, we've just learned how to find the area under a graph that is a straight line or has visible edges. So we know how to find the area under the curve for this graph. We know how to find the area under the curve for this graph. We don't know how to find the area under the curve for this graph though. So that's where integration, which is another concept, or the second concept from calculus, and that's where it comes in. Integration is the ability to be able to find the area under a curve, usually an instantaneous rate of change curve, where the gradient of the curve is continuously changing. Now, an easy way to approach this would be to try drawing rectangles under the curve. So, if I were to draw rectangles to try and estimate the area under the curve, we would get an answer, that's for sure. But you would realize we're missing out on a lot of space, like right here, right here, right here, right here, and all of this. So that's why we need integration. Integration is a mathematical tool that helps us accurately get the actual area under a curve. Because for this straight line graph right here, we could just find the height of the graph, so the change in y, and the breadth of the graph, so that would be the change in x. And we could just use the formula of a triangle, so half into breadth into height, and we get the area of this section under the graph. Whilst over here, we would have to use integration. Now in this video, I won't be looking into integral notation yet. Once I complete differentiation altogether, or most of it, I will begin making videos on integrals or integration. And that's where I'll introduce you to the integral notation. Why do I choose to not teach you this right now? It's because people can get really confused with which one is for integrals and which notation is for differentials, for derivatives. So, to summarize this video altogether, we use differentiation to find the gradient of a certain point on a curve. That could be the instantaneous rate of change curve. And we use integration to find the area under the curve, which can be extremely useful, like if we're trying to measure the motion of a car, so we know the speed and the time elapsed of the car. We know that the area under the curve would be its distance. So integration helps us calculate that distance. I hope you enjoyed this video and I hope you were able to learn something out of it. Thank you for watching and see you in the next video. Bye.